12.
Okay, let's start with this. So I'm going to talk about Hamiltonian simulation, and we are going to go through a series of seminars. So in the end, I want you to introduce all the techniques that are in this field. So let's begin with one of the most basic concepts, which is the quantum random walk. So today I'm going to introduce you the importance of quantum random walks, just for the purpose of Hamiltonian simulation. So, as I have said, we're going to talk about Hamiltonian simulation, and let's suppose that we are given a Hamiltonian, obviously as a discrete matrix, because we are on digital computers. So we have a certain Hamiltonian which is given by a matrix, and our task is to simulate. What do we understand as simulating? So basically simulating a Hamiltonian that so far we are going to suppose that is time independent, is going to be to approximate the evolution of any time for a unitary, such as the error with respect to certain norm, let's say norm 2 is minor norms. So we are given this matrix of our Hamiltonian that may be a matrix on the space of matrices of 2 to the n to 2 to the n, because we are assuming that we have n qubits, and we want to calculate this. But forget about this today, we're not going to go that far.
What's U?
A unitary. So this is what we want to implement. This is the unitary that we are going to implement, that is going to approximate the exponentiation of the Hamiltonian. But we are not going to implement this unitary today, or at least the whole unitary. So, just to be clear here with the notation, there are 3 different schools when simulating Hamiltonian. So roughly speaking, we have 3 branches. One of them is the product formulas. So you may be familiar with product formulas as Trotter decomposition, Lee-Trotter decomposition. So basically, we calculate the exponentiation by using this kind of product formulas. The other school is sparse Hamiltonians. This is the one that we are talking about today. And the third one is the combination of unitaries. So we're going to be focused on sparse Hamiltonians. So just to have the notation, the rows are going to be designed with index J, the columns are going to be designed with index K, so this index is going to be from 1 to 2 to the n, the columns is from 1 to 2 to the n, and because we are dealing with sparse matrices, we are going to have the sparsity index. And the sparsity index is going to be L from 1 to D. So we have D sparse matrix. And we may have some entries.
So what's the sparsity index? How is it defined?
Basically, we assume that we have non-zero elements. So we in every row, basically we assume that the number of non-elements goes from 1 to D. And this is because we are going to have an oracle that given the first or second or third or in general the 11th non-zero element of a given row, we're going to have an oracle that is going to return us which is the column index for that value. I'm going to explain it right now. So basically, we are going to have this Hamiltonian, and we are going to have an oracle access to this Hamiltonian.
Lower the sparsity index, higher the sparser the matrix, right?
Sorry?
The lower the sparsity index, the more sparser the matrix is, right? So if it's 1, it's super.
No. The sparsity, I mean, the matrix is going to be D sparse. But I have D non-zero entries in every row. So this is going to be the L equal 1, this is going to be the L equal 2, and the last one is
it's
going to
always
be
the same. So
Yeah.
every row and every column
Have
the elements.
Yeah, every row has the non-zero components, and I'm going to basically order these the non-zero elements with this index.
And it's only applied to the rows or also to the columns?
We can assume it's only for the rows.
Okay. So they are like blocks, right?
Yeah.
So if there is two sparse matrix, then L equal to 2 for each row is a non-zero entry. That's what it means. So capital E equal to 2, let's just say.
Yeah.
And L equal to 2 for every row is a non-zero entry.
No. They can be different.
Two non-zero elements in a row.
Oh, okay.
Because
So
okay.
So L1 may correspond to different columns.
Yeah, L1 is associated to J.
Okay.
So,
okay.
so I'm going to explain it with the oracle access. It is going to be much more clear right now. So basically, the oracle access is going to be given by two oracles. So first we have the finder oracle. So this oracle is going to act on a space of n qubits here, another space of n qubits here, and basically we're going to introduce to this oracle J, which is going to be the index of the row, and L, which is going to be the index of the non-null element that we want. And this oracle is going to return us basically J and K, where K is the position of the non-null element. So basically, we are feeding our oracle with a column and one of the values of the sparsity index, and it's going to say, hey, the element, the non-null element in this row is in the 3rd, 5th, 7th position. So that's basically what we want. This is our first oracle. So this oracle is going to be the first one, and we have a second oracle. So basically, just to make it clear, this is what we have.
Just one question. Did you already stated the problem you're addressing or not?
The problem that we are addressing, no, I am.
You're just like introducing something.
Yeah, I am introducing all the notation needed.
Okay, thank you.
The problem, in the very end, the problem is to do the Hamiltonian simulation.
No, that's fine.
Yeah.
Just to listen. Okay. Thank
I'm
you.
only giving you the elements of this.
No, that's fine.
Okay.
Sorry.
So basically, we have this oracle, and this oracle is going to be from this space to this other space. And the only thing that you have to take into account is that here you have much more less elements than here, because actually this index is not going to be that large, but it's completely fine. So the second oracle that we have is this. So now, given the coordinates of a certain element of the matrix, this oracle is going to give us the element detected. So basically, this is going to have n-bit representation. And with these n bits, we may represent any complex number with real and imaginary part, and up to the precision that we want. But the thing is that we are using this number of resources here to encode the value of the Hamiltonian. And this is how we can access to our Hamiltonian.
So it's age applied to it? What is it again?
This
Yeah.
is the entry in that value. So basically,
Okay, thank you.
okay,
Yeah, I got it.
okay, who is here? The element matrix.
It's a complex number encoded somehow.
You encode the real part and the imaginary part with a certain precision, and maybe in a polar way, whatever. The encoding is not.
Javi, what's the difference between JK and L? I mean, L, what is that? The number of the non-zero
Okay.
element in a row?
Let's take an example. So imagine that you are given this Hamiltonian. So you have j equal 1, and let's say that in this case d is equal 2. And if, for instance, I ask for the L is going to be 1 and 2, and basically when I use the first oracle with 1 2, this is going to return me 1 and 4. And then when I fill with 1 and 4, this is going to return me 1, 4, 5. Okay?
That's the second one.
This is the OF, this is OH. Okay. So, just to give you an example of this kind of, well, a couple of things before going to the next thing. Obviously, I have defined this on a single input, but you always have to have in mind that these oracles can act on superpositions. So basically, they are going to act on all the combinations when feeding these oracles. So this is the magic of quantum computing. Okay, do not forget this.
Why do you call it OF and OH? Is there a kind of
The oracles,
yeah,
Finder and Hamiltonian.
finder and Hamiltonian? Okay.
Okay. So why are we interested in simulating these kind of matrices? I'm going to give you an example, and I hope that this is convincing. So imagine that we are dealing with continuous variables, and we have a grid of points. So we have an interval, and we have to somehow calculate this interval to a maximum and minimum values, and we are going to discretize this continuous interval, and we are going to have this size of the grid. So basically, when simulating a Hamiltonian, let's say a really simple one, which is the harmonic oscillator Hamiltonian, which is this, we are going to define discrete operators, and these discrete operators are going to be given by, for instance, in the position basis, these couple of matrices. So as you can see, for simulating the Hamiltonian of the harmonic oscillator, we have two sparse matrices, and for this one, the finder is basically obvious because we only have d equal 1, so in this case it's really simple. And the entries of the Hamiltonian are going to be a linear function because basically this value is going to correspond to this function. So this is a function that we have to encode into a Boolean register right here. And for this other case, we have to give the position of the ones and minus ones and the value of it. Okay, so this is just an example for you to know why it's important to simulate this kind of Hamiltonians, because when simulating continuous variable on a quantum computer, you have this kind of operators. And these two are the values of the boundary conditions that I have not picked. But for instance, this will be a -1 and a +1 if you pick periodic boundary condition. That's important. Okay, so that being said, I'm going to introduce you what a quantum random walk is and why it is important. So now that we have our Hamiltonian, let's think in our Hamiltonian as a graph, such as every entry of the Hamiltonian, every row, given a row J, we imagine that the values of this row are going to give us probabilities of going from the node J to the different possibilities, so 1, 2, 3, 4. 1, 2, 3, 4. And, well, this is a self-loop, actually. So imagine that these values here are probabilities. Obviously, the entries of a Hamiltonian are not minor than 1. They don't sum up to 1. They may be complex, but we can do an operation on the Hamiltonian, so we can think about this as a graph. So basically, every row is going to give us the probability of moving to the corresponding node. So basically, we have to think of our Hamiltonian as a probability of transition. And this is more than less the idea behind the quantum walk. So basically, we're going to understand our Hamiltonian as a matrix that is going to give us the probability of going from J to 1 itself, from J to 2, from J to 3, the So that's the idea, and now I'm going to be a little bit more rigorous on this. So yeah, actually, how can we do this? Basically, what we're going to do is to use this norm, which is going to divide per the sum of the absolute value of the elements of the row, and then we're going to apply the square root of the element. So that's what we're going to take as part. But I'm going to explain it a little bit. I just wanted to give you an intuition.
This is already the metric used to obtain the pseudo probabilities of the graph.
I'm going to build an state from the matrix, and this state is going to be interpreted as if we're using the matrix as a probability of transition.
And that's given by this sum, right? This probability.
Yeah, but I'm not going to build this matrix exactly. I'm going to build an state. But this state is going to take the transition probabilities from the Hamiltonian in this way.
But will it make transition probabilities or transition amplitudes?
We are going to have amplitudes, in fact. Yeah, it's tricky, but the idea is that we are going to take every row of the Hamiltonian, and from every row we are going to build transition amplitudes. Yes?
If you're going to interpret as probabilities, would that mean that in the end you're just going to consider measuring on the basis in which you're transforming? Let's say in the eigenbasis or whatever transformation you do.
And what is the eigenbasis?
I don't know, whatever you say.
That's going to be why it results into Hamiltonian simulation, or kind of. Because if we take the Hamiltonian and we understand that moving the values of the computational basis according to the Hamiltonian with those probabilities, when we go to the eigenbasis of the Hamiltonian, we're going to have that those are like the distribution on the eigenvalues of the Hamiltonian is going to be somehow the stable distribution. So we're going to have a Hamiltonian simulation process. Kind of. But I'm going to go a little bit further. Okay.
Javi, I know this is not so important for you now, but I still didn't understand how you define this system, which is the output of this OH. You have this cat H.
This here.
Yeah.
This is an oracle. This is given.
Yeah, so I understand what you mean by cat K, because I know K is just like a discrete variable. So you have just a simple like T-level system. But if you have like because this H, JK can be any value.
Any value, yeah.
Complex number. So what do you mean by cat H?
Well, basically, you have a couple of values. Actually, imagine that you have a function of j and k.
Can I ask, the question is, how do you represent the complex value hjk with m bits? Or not?
Can I write?
Yeah, sure.
I'm gonna write there so I don't start your presentation, but like I understand that what you mean by this. So if k is like 1 up to n, so this is just like
Take up to 2 to the n.
yeah, but it doesn't matter like any values. I didn't use another letter. So this is just like this, right?
No. Yes. Well, I'm encoding information into the bits. So basically, when I have k or 3, for instance, I'm going to have like I know 1, 1. So for m equal 2, I have k equal 3. And basically, I have to compute a Boolean function on this input.
Okay, but I would say this is a different thing, how you represent this as bits. Like if you have n values, so this is a vector.
Yeah, this is
a
a vector
dimensional,
but I'm not
complex vector space, right?
Yeah, that's right.
Is it right?
Yeah, but I'm not using the vector, I'm using the values.
But then if you have like something which is like now a label which is not like a discrete value, how do you represent this as a vector space?
But this is the
Because your state needs to be a vector in a complex vector space.
yeah, but I'm using the number of rows and the number of columns, and this goes from 1 to 2 to the n. value will be 4 plus 25, so this is 29. So this, in this case, will be the binary string corresponding to 29.
And what is the relation between this H and this F?
Well, in this case, you have a given Hamiltonian, and the entry of every value Hamiltonian is given by the index of the row and the index of the block.
Yeah, I think. Now I get it. Can I?
Yeah, sure. Okay.
Right. And when you said that you interpret the Hamiltonian as transition probabilities, if the entries are complex, as you define the.
I'm going to do. It's not that easy.
Also,
Actually, it's an amplitude probability. So basically, the state that I'm going to define to do the transition and to do the quantum random walk is going to be kind of this. So basically, when you multiply per the complex conjugate, you are going to have this, and that's going to be real and positive. But it's a little bit more tricky.
Also, if you talk about transition probability, so as the elements of the Hamiltonian, so then you have to define a basis, no?
What do you mean with define a basis?
So basically the matrix elements of the Hamiltonian is.
Yeah, you have the computational basis. We are working
So
on.
you're talking about the Hamiltonian is already the computational basis.
Yeah, or any basis you may want to work with.
and are you going to multiply by normalization factor?
Yeah, the normalization factor is going to be this norm of the Hamiltonian. Okay, let's continue. So, first I'm going to introduce you the quantum random walk. So, the quantum random walk basically is going to evolve a probability distribution. So, classically, when you have a particle, a random walk is going to decide whether the particle goes up or down with a certain probability. In this case, as we have a quantum state, we have a probability distribution, which is basically the superposition of eigenstate, and this is going to evolve given a certain step of a unitary. So, basically, every step that classically corresponds to the particle going up or down, in our case, because we have a probability distribution given by the superposition, is going to be given by a unitary. And this is the unitary of the quantum random walk. And it's defined as follows. Okay, it's a little bit tricky, but I'm going to go through all the details of this. So, this is 2 e dagger minus a. This is the unitary of the quantum random walk. Every step of a quantum random walk, every time we have to define whether the particle is going up or down, classically speaking, we have to apply this unitary. So every step is going to be given by this unitary. So how to understand this unitary? So first, in order to be able to create a quantum random walk, we need some extra elements. And the first thing that we are going to do is, okay, let's imagine that we have an initial state to which we want to apply the quantum random walk. So basically we want to apply this unitary to our initial state. So in order to apply this unitary, what we are going to do is to expand our space. So let's suppose that we have a state which is given by this, and we want to apply this quantum random walk. So basically to calculate the application of this, what we are going to do is we are going to expand this state, which is living on a space spanned by n qubits, to a state which is expand to n plus 1 qubits. So basically, in this second register that I have added here, I'm going to create this state that is basically going to give us, which is the probability of going into a transition from J to every possible value of K. So this is going to be a superposition such as for every value of j, I'm going to encode the transition probability from this j to that k. And in order to do everything right, we need an extra ancilla. So there is going to be an ancilla that we need for this, and we have transitioning from rows to columns. So what is this? File j? Okay. So yeah, just to make it clear.
Javi, one stupid question.
Yeah.
Between the two J texts, is that a J or a semicolon?
Semicolon.
Thank you.
So we have added the space of case. We have the initial space of case in which our state is represented, the space of case, and the ancilla. Okay. So now, what is this? Yeah.
Sorry, this thing you just wrote. So this is what the quantum walk is going to do. Go from the down state to the one on top.
No. This is the, just to understand where this state is going to be in. This is going to be in a Hilbert space, such as I use the first n qubits to encode the values of the rows, the second n qubits to encode the values of the columns, and the ancilla. Because
and the ancilla is going to contain the probability of the transition.
No, I'm going to. The ancilla is needed because when you normalize, you have some additional probability that must go to the ancilla. I will go through that, but it's not that easy. So basically,
Javi, did you explain what V is, or?
I'm trying to do it. Okay. So the first thing it is, and what I want to make clear in all of this step here is that we have our state to which we want to apply this. So basically we want to apply to this unitary that is going to map this into another state after applying the quantum random walk. And the quantum random walk has to be understood as a transition from some vertices of our graph to other vertices of our graph. So the way of doing this is, okay, I have initial vertices here, which are the rows, and I'm going to add the end vertices here, and I'm going to encode the probability of transition in this kind of states. And I'm going to do some magic tricks, and suddenly we will have what we want. But it's not that trivial in engineering. So basically, this state is going to define as follows. We have an epsilon, and I will explain what this epsilon is. We have the norm of H. We have the sum to the n square root of. So the idea here it is basically that given a row of our Hamiltonian, what we are going to do is, okay, let's normalize the values so we have kind of a probability distribution with the norm H1. Just to remind you, the norm H1, it is the maximum over the rows of the sum of the absolute value of the elements of the row. So basically, if I normalize with this, now the absolute value of these elements is going to sum minor than 1. Yeah?
But your sparsity is defined in the rows, so you could have to add like exponential terms to obtain that norm, right? So is there a problem if you don't have an exact value for it?
You can have a bound.
Okay, and with a bound, the algorithm works.
The
somewhat
algorithm
better.
works. That's in the, I'm not going to go into too many details, but yeah, you can have a bound for the norm. But so far, let's assume that we have the norm of this. Okay, so basically, as I am using this norm, the sum of the absolute values may be also smaller than 1. So we may have some remaining values because the maximum may be only reached in a single column, in a single row, sorry. So basically, that's why we use the ancilla, because we may have some extra probability that we are going to give here to this other state, which is going to be using the same norm for every row, maybe some rows are summing less than the norm, the Hamiltonian. So that probability goes to the ancillary term. Yeah?
Is the ancilla cubic?
Yeah. Ancilla is a cubic with values 0 and 1. Okay, well, actually here I have a superposition I don't really care about. Okay. So I'm going to show you how to build this state. But
Sorry, Javi, I think it would be really helpful for me if you briefly go over again over the state.
Over the
explain
state.
What
Okay.
each thing is.
okay, let me erase
So, for
this.
example, what's the epsilon?
I'm going. Okay, explanation, because this is the most tricky part, and once that we have understood this, we are done. Yeah, basically, that's it. So, okay, I have, let's make this with an example. Okay, so let's have a Hamiltonian. And imagine our Hamiltonian is 1, 2, 0, 0, 5, 2, 0, 0, 1, 2. Okay, so basically here I'm encoding the square root of the conjugate value of the given Hamiltonian. So the thing is that I have not still show you, but when I multiply this per the complex conjugate, I'm going to calculate something of the form this is I think it's kind of this, I don't remember now, but that's going to be proportional to this. So basically, when I do the operation that I have that I still have to implement to this state, this term with the brag term is going to give us the corresponding value.
So that square root is doing the job of the amplitude.
Yeah, this is going to be the amplitude, and obviously this is normalized because I have divided per this value. So in this case, this value is 8. H1 is 8. So when we normalize this with 8, we are going to have that some rows are not going to sum up to 1. And because this does not sum up to 1, I need an ancilla to encode the remaining probability. In this case, 3/8 is going to go from the second row to this ancillary unit. And this epsilon here is a value between 0, 0 and 1, which is going to give us what is called laziness. Because if we take epsilon equal 1, we will have a pure discrete quantum random walk. But if we reduce epsilon, we are somehow making this slower, and we are reducing the probability of transition. So this is called the laziness parameter.
So it's like the probability of doing the other thing.
Instead of using the one, instead of doing the random walk.
And the other thing, sorry, because I cannot see well what are those gates.
Yeah, this gate is 1, and this gate is a superposition we really don't care about. Whatever. Okay, yes, it's tricky. Okay, so now, important thing. We have defined this weird state, and it's struggling. And now, why is this state important? This state is important because it has the following property. Now we have two subspaces because this state is living in a space that has n with j, n with k, and then 0. So basically, when I compute this, this operation, this is going to be, actually this is the square root of be something which is proportional to the entry of the Hamiltonian. That's what really matters here. That building this state and calculating the expected value of the swap operator of this state, we're going to get an operator which is proportional to the Hamiltonian if we want to calculate. It is a little bit tricky how to define actually this square root, but I don't want to go to many details. We can discuss about this other time. But the square root, if you have a non-negative value, can be defined into a standard value, such as the square root of as complex number is the square root of the modulus and half of the phase. And if it's negative, you have to apply a trig, but it's not really relevant. So, okay. So now it makes sense that we have this swap operator here acting on this enlarged space. And now we need to understand who is this reflection or this T operator. And this is the last part. So T basically, it is the sum over J of this. So basically this is an isometry that is making this enlargement of the space. And basically from J I'm going to J, well, I'm missing this. So basically from J I'm going to J side. So this is enlarging the space. And actually here we have a reflection. And a swap operator. Okay. And now the magic properties that you are.
Sorry, what is S again?
What?
What is S?
S is the swap operator.
Swap, okay.
Swap.
Okay.
Swap. So basically you have a swap and a reflection under this isometry. Okay. And now here's where the magic comes. So basically, okay, now to erase something. I'm going to erase the arrows. The property that you have to strongly believe is the following. I'm not going to check it. But with this given construction, let's go back to our Hamiltonian because so far we have not talked about it. And in the end, our Hamiltonian can be diagonalized and can be written in a certain basis with the eigenvalues. This is the composition of our Hamiltonian in the diagonal form. So actually, this is going to be kind of
in this diagonal Hamiltonian, are you missing the bra or just like the?
I'm missing it.
Okay. Suddenly it's a vector.
Yeah, and this is going to be kind of the Hamiltonian resulting from here is going to be proportional to our original Hamiltonian. So the thing now is that if we take the basis of eigenstate of our Hamiltonian and we apply T to an eigenstate of our given Hamiltonian, we are going to obtain a superposition of two states, which we will call lambda max and lambda minus. And what are these lambda max, lambda plus, and lambda minus? I'm not going to give you a description, but you can calculate them. The thing is that these two guys here have eigenvalues. Well, no, not yet, not yet. These two guys here eigenvectors of the quantum random walk. So basically, we have that an eigenvector of the Hamiltonian, eigenvector of H is mapped to an eigenvector of the quantum random walk here. And the eigenvalues of these are the following. Okay, this is really important. So this operator, based on these weird states, is mapping us from eigenvectors of H to eigenvectors of the quantum random walk. And the eigenvalues of the eigenvectors of the quantum random walk are given by this. And actually,
Sorry, I mean, there's this expression. What is lambda 2t?
the what? This?
Lambda tilde.
Lambda 2t.
Oh, I forgot. Lambda tilde, it is this one.
Okay, and the pi? What about this pi?
I.
Pi.
Pi.
It's not one pi.
Yes.
So this is pi, okay.
Yeah.
One minus.
And minus plus 1.
Minus plus 1. Yeah, if you have the plus, this is plus, minus.
And what is it? Just largely, I don't understand the expression. I cannot read it.
I understand that if you have a minus, then it's 0, but if you have a plus, then it's 2 pi.
Yeah.
With this
2
2 pi,
pi
it's 0.
Basically, this is a minus here. Okay, if you want
No,
instead
but
of
then you need a, no?
Uh-huh.
You need to divide by half something.
what?
If you add 2 pi to the face,
Yeah.
you are doing the complete loop.
Well, it's not. It's pi over 2.
Okay, thank you.
What I don't understand is probably because it's written by hand. I just cannot read this expression in the brackets. 1 minus plus something. What is it, the something?
It's a 1 again.
It's a 1 again? Ah, okay.
Yeah. This is 1. 1.
Nice, okay. Sorry.
Okay. So now the thing of doing this simulation, there are like 2 tricky parts here. How to build T. Here you have it. On the next page.
Wouldn't it be easier to put the plus minus before the
No, I want this as a phase because what happens? Okay, let's apply.
I know you have an answer because there must be an answer to do this.
Okay. Yeah, I'm finishing. I promise.
Okay.
So basically now the idea is what happens if I take an initial state in this and I then apply the quantum random walk. So basically, if I have an initial state, let's say C0 decomposing to the eigenbasis of this, I'm going to map this to with T. I'm going to map this to and then when I apply the quantum random walk, I'm going to have here exponential plus pi arcsin of lambda plus and So basically, we have this mapping of the isometry that for every state of the Hamiltonian maps is to this superposition of the eigenstates of the quantum random walk, and then because these two are eigenvectors, I will have the eigenvalues.
Question. I've gotten to the point where following the math is hopeless for me, but what does lambda plus and lambda minus eigenstates physically mean?
Physically,
Yeah. Is there a way to say what they what makes it lambda plus and what makes it lambda minus? Is it, I don't know.
In your
Positive and negative space
transitions,
transitions.
like in your graph, is there a meaning for these states?
not really.
Because what it does is more like it tells you is evolution, right, in the graph or something. So maybe these eigenstates means like your transition goes to a specific direction or something.
Yeah, I wanted to
Something like
different,
that.
but yeah, I don't know.
I thought these are the states that just stay the same.
Guess what?
Aren't these the eigenstates of V or no?
Yeah, I mean,
Yeah.
lambdas are eigenstates of H,
Just like
but what distinguishes plus from minus? What does
Ah, well,
Just eigenstates of V. Right? No. Yes.
plus and minus eigenstates of B.
Of V, yeah. They are eigenstates of the quantum doesn't work.
Okay, so the lambda the eigenstates of H are also eigenstates of B.
No, the eigenstates of H are transformed into eigenstates of V through the isometric
Okay.
I mean, they're just from each a superposition.
Yeah, that's a
The
composition.
dot and each
Yeah.
one eigenstate.
Yeah.
Okay, yeah,
F
that's
of V
Thank
is
you.
actually this, no?
Yeah.
eigenstates.
Okay. So
Then maybe they are like some.
the next step here that we would like to apply is T-dagger. But we cannot apply T-dagger because the phase of this guy and the phase of this guy are different. Because if we have the same phase for both, we can basically have it as a common as a global phase, yeah. We can subtract this as a global phase that is going to be a phase of lambda, and we can basically do the opposite transformation and basically the superposition of these two eigenstates is mapped to an eigenstate of the Hamiltonian. So the thing here, and this is going to be the next episode, is how can we transform this amplitude and this amplitude to something that is going to allow us to do the transformation T-dagger. And the answer is pretty simple. Just apply the transformation sin of x. Because the sin of this, it is this. And the sin of this, the sin of the arc cosine of lambda tilde is lambda tilde, and the sin of the minus the arc sin of lambda tilde plus pi, it's also lambda tilde. And after this transformation, you get something which is a lambda over square root of 2. And the Hamiltonian simulation is done.
Why can't you apply to that?
Because you're not going to obtain the desired state.
What is it, the desired state?
The initial state is this, A lambda lambda. And basically the target state is whatever. Yeah,
This
so,
is evolved under the Hamiltonian.
right.
That's the only thing.
This is evolved. Our target is evolving with the Hamiltonian. So basically, to be able to map this into this, we need both to have the same phase.
So this is the evolution of this Hamiltonian system?
This is
or
the
unit
state
of time, let's say.
Well, I am missing some things here. I can add a T here in the transformation, so I have the insert time.
Yeah, honestly, I use a PP unit time. But
And when is the evolution happening in the process you mentioned in the...
We still don't have the evolution here, but the evolution is these 3 steps. Well, actually, we need to apply T, then this, then quantum signal processing, and then T dagger.
So you just do transform and then go back and you have like a problem. Why? I mean, you did nothing to the state.
Yeah, I did. I applied operators.
Yeah, but you didn't evolve the state, no?
Doing this transformation is equivalent to evolving the state with Hamiltonian.
yeah,
Okay.
it just prepares the state you want by doing this quantum signal processing.
The quantum signal processing is basically enabling me to do this transformation here. This is for what quantum signal processing is.
And is it like just a random unitary?
No, it's much more complicated. It is another thing.
Okay.
So let's go back briefly to this. So forget about this last part. The important thing of the quantum random walk for Hamiltonian simulation is that after applying these 2 steps of the isometry and the quantum random walk itself, we get a Hamiltonian values. And this is going to be the starting point for later on applying more operators. And the tricky part here is, okay, how easy is to implement T? Because in the end, T, it's the key part here. Because for implementing the quantum random walk operator, we only have swap and T. And T, it is as easy as preparing this monster. But this monster can be prepared by using these 2 guys. Easily.
How is it easy to prepare those 2 guys? Very difficult.
With these 2 guys and more than 1 complexity, I can prepare this guy.
And how do I prepare those?
And that's
why they have
Oracle.
oracles, you know?
Yeah.
You just like hide the
Yeah,
typical
it's
function
function
of black box,
right?
Yes, that's like.
It is a black box, I have like it is quite good. Actually, that's one of the challenging things. Given one of the challenging things in theory is, okay, let's say that I have a couple of Boolean inputs here, and I want to compute a function of these 2 Boolean inputs here. Let's say f of jk. Doing this operation, we know that classically is done, because on a digital computer, when you have a function of 2 variables and you compute it, if you have an analytical expression for it, this can be efficiently done in polynomial time, because it's how computers work. So we don't really worry about this. We assume it can be done.
So polynomial time.
Polynomial time.
In the size of the Hamiltonian, I suppose so.
Yeah.
Okay. So not so difficult then.
It's not difficult, but it's not explicit. How to build these oracles is another lecture for another day. But the important thing here is that with these oracles and with the quantum random walk operator, which is this operator here, you can build something that is preparing a state that is almost the Hamiltonian simulation. Almost. But you need to apply some techniques here to achieve what you want, which is the exponential. This.
Why do you mean almost? Because it looks like it's precisely the same state, no? You need.
I mean, I have to apply T dagger and obtain what I want. If I apply T dagger to this state, I'm not obtaining evolution.
So your quantum signal processing cannot be done like that perfectly. That's what you mean.
No, it can be done. I have not explained quantum signal processing.
I mean, so if you can like perform this operation, then you apply its dagger and you get the very same state as you needed, right? Is it the case or?
Well, we got this state, okay? This is a state that we wanted to get today. Okay. So I cannot apply T dagger to this state. If I apply T dagger to this state, I'm not going to have my desired state, which is this.
Okay, yeah.
I'm not going to do it. I need something in the middle.
Yeah.
Because I have the arc sign and also the faces are different. This is known as the sign problem because the sign of this guy is what is not minus. The sign of this guy is not the same sign that this other guy. And yes, up to here, this is what I wanted to tell you today. And the next part of how to transform faces is called quantum signal processing.
Okay.
But quantum random walk is basically this operator. I do not want to explain quantum random walks itself. I want to explain how to use quantum random walks to generate Hamiltonian simulations. So basically, with a Hamiltonian, building these two operators, the isometric T and the operator of the quantum random walk, from an initial state, I can obtain this state. This is the important thing. And operators T and V can be easily achieved by using these two operators. That's the image. Okay?
So is it like a first half of your presentation?
Is it?
Is it the first half of your presentation?
Well, yes. The next step is using quantum signal processing.
And then we're gonna have another one.
Yeah, another day.
I like it because then we have two presentations. Cool, man.
Yeah, I can go into the details, but I think it's better.
No, yeah, very good, very good.
Okay.
Thank you, Javi. Very nice.